Welcome to the Deep Dive. Today we're getting into something that honestly feels almost philosophical. We're talking about the very foundation of modern AI. For decades, the dominant religion in reinforcement learning has been this thing called the reward hypothesis.
Right.
The idea is, well, it's simple, that all goals, all intelligent behavior can be boiled down to one thing. An agent trying to maximize a single score,
Yeah.
a number.
Just a single scalar signal.
Yeah, exactly. But the research we're looking at today makes a groundbreaking argument that this hypothesis is fundamentally broken.
It's more than broken. It's actually in conflict with creating the kind of AI we really want. Flexible, compositional, and this is big one interpretable general intelligence.
So it's not just a new algorithm, this is a proposed paradigm shift.
It really is. I mean, think about the world you navigate every day. You're not just going from point A to point B. You're managing your energy, avoiding traffic. You have to remember you have a meeting all at the same time.
Yeah.
How could one single number possibly capture all of that? So the core question these researchers are tackling is, what principles really underpin flexible, goal-directed action in these, high-dimensional worlds?
Because the old framework, the standard Markov Decision Process, it just doesn't scale. Not elegantly, anyway.
No, not when you get beyond simple robotic tasks. It just falls apart.
So our mission for this deep dive is to unpack this unified theory that says, okay, let's replace that reward signal entirely.
Get rid of it.
And replace it with this concept of feasibility. This is the key pivot, right?
Absolutely. Feasibility is just. What's the probabilistic likelihood of achieving a specific goal while, and this is crucial, while also avoiding a set of critical constraints?
And this new framework, the Task Markov Decision Process, or TMDP, it's built to guarantee the AI has three essential properties that reward maximization just always seems to struggle with.
Right. The first one is compositionality. So the ability to take basic, simple actions primitives and stack them together, like Lego blocks.
To build complex, reliable, long-term plans.
Exactly. Then you have modularity. So the system can, break down and reuse knowledge and representations across totally different tasks. It doesn't have to relearn everything from scratch.
And the third one, which feels more important every day for safe AI.
Interpretability or verification.
Yeah.
It just means the plan the AI creates can be read like a map. It has to clearly show what events an agent might cause before it ever takes a step.
Because if you can't verify what the AI is going to do,
you can't trust it. Simple as that.
Okay, that's a powerful summary. Let's break this down. We have to start with why. Why did decades of relying on reward maximization become such a barrier to these three goals?
Well, the problem isn't reinforcement learning itself. It's really just the reward hypothesis. As soon as a problem scales up, to the complexity of a dynamic, open-ended world.
Like trying to beat a game like The Legend of Zelda versus just playing Pong.
Perfect example. The idea of just summing up a reward signal becomes an active hindrance. You get these really brittle solutions.
And the most immediate, and I think critical, failure point that the researchers just hammer home is the total loss of interpretability. Why does maximizing reward kill our ability to understand what the AI is even trying to do?
It's baked into the math. The standard Bellman equations, which are used to calculate the value function, they basically just aggregate all future rewards and costs into one single running number, an expectation.
It's like looking at your credit card statement and only seeing the final total, not what you actually bought.
That's a great analogy. You know the final expectation, but you lose all the specific semantic detail. You lose that crucial spatiotemporal information about when and where a reward event happened, or even more importantly, when a constraint violation happened.
So we don't know if the high score came from 3 easy points early on, or one really hard point right at the end. All that planning data is just gone, lost in the sum.
Exactly. And for a verifiable system, you need that detail. You have to know if the agent is likely to violate a safety constraint in 10 seconds or 10 hours and where that might happen. The value function just turns all that rich, useful information into a single, meaningless number.
Okay, so if the old way destroys the data we need, we have to throw out the reward signal entirely. How do we model goals without it? This is where they introduce the Task Markov Decision Processes, the TMDPs.
Right. And TMDPs are actually simpler to grasp. They shift away from maximizing a reward and instead just use two probabilistic tests.
Two tests.
You replace the reward with a goal function. What's the probability a goal is satisfied? And a constraint function. What's the probability a boundary is not violated? That's it. A task is just reaching a certain goal probability while staying inside your constraint probability.
And to solve this, they introduced something new again, the Option Kernel Bellman Equations, or OKBEs. It sounds like they're designed to completely bypass that old value function.
That is precisely what they're for. The OKBEs aren't for value maximization. They're for program synthesis. They construct a plan that maximizes goal reachability while strictly avoiding constraints. They go straight for feasibility, not some abstract score.
And this new kind of optimization, it must produce something very specific, very detailed if it's going to solve that interpretability problem. What's the core product that comes out of these OKBEs?
That core product is called the state-time option kernel, or STOK. And you should really think of a STOK as a kind of verified, high-resolution, predictive map.
A map. Right.
It's an initiation-to-termination kernel for a policy, what we call an option. It maps where you start to where you'll end up. And this is the key, how long it took to get there.
So the STOK is the detailed receipt, not just the final sum. How does it preserve all that spatiotemporal information that the value function just smeared out?
Because it's not calculating an expectation, it's calculating a probability distribution flow. It propagates probability mass back through the system, so it preserves the event probabilities.
Yes.
And the STOK itself is made of two subfunctions. You have the state-time feasibility function, which records when and where you succeed, and then the state-time infeasibility function, which records the flip side, when and where you fail or violate a constraint.
That level of detail sounds like a huge step for safety. But it also sounds a little familiar. For anyone who follows computational neuroscience, this is a bit like the successor representation, right? That map of future states.
It's a great question. And yes, the field has looked at predictive representations like the SR for a long time. They're useful, but they're generally not truly compositional.
What do you mean by that?
Well, trying to stack two SRs is like trying to tape two maps together. The uncertainty and the averaging just accumulates, and the combined map kind of falls apart. It's not clean.
So the knowledge isn't modular? You can't really reuse it in long chains?
Correct. And this is where the STOK is, well, sort of revolutionary. It's designed for compositionality. They are perfectly stackable pieces of knowledge.
Okay, let's talk mechanics. How do they compose so cleanly?
They use the foundational math of prediction, the Chapman-Kolmogorov equations. So if you have a CAO for a simple option, say all dollar like crossing a room and another for $2 opening a door, you can mathematically compose them with a simple operator and instantly get a brand new STO for the abstract action, crossing the room and opening the door.
A meta policy.
Exactly. So the agent can make these really complex long horizon predictions just by stitching together these verifiable little kernels. You don't recalculate the whole problem, you just link the verified pieces you already have.
That's incredibly powerful. But now we have to talk about the real world. We're talking about high-dimensional problem systems where everything is coupled, where one choice affects, 10 other things.
Right.
An agent's position, its own internal state like hunger or hydration, its inventory. When you couple all that, the state space just explodes, the curse of dimensionality.
And that's the exact challenge they built the next piece for, the compositional TMDP, or CTMDP. To show how it works, they use this great example, the honey badger agent.
The honey badger, tell us about it.
So imagine this honey badger has a complex task, like getting honey in flowers, but it also has to regulate its own body. So you've got three coupled systems.
Okay.
There's the base level grid world, where it physically moves. There's its hydration space, managing its water levels. And a logical space, which tracks inventory, like, do I have the key?
So a massive coupled system. The total state is the multiplication of all three. Planning in that combined space seems impossible.
Conventionally it is. And what links them all is this affordance function. It's just a probability function that says how an action in one space affects another. So drinking at the lake, a base level action, affects the high level hydration space.
And this is where the paper pulls out its big computational trick.
Yeah.
The STOK decomposition theorem. How does that deal with the honey badger's ridiculously complex world?
This is the core solution to the curse of dimensionality. Instead of trying to calculate one gigantic high-dimensional STOK for the whole coupled system, the theorem proves that it factorizes. It breaks apart into smaller pieces that can be solved individually.
Wait, hold on. If it factorizes into smaller pieces, that means you're avoiding having to compute anything over the entire product space. So you're turning one impossible calculation into a bunch of smaller solvable ones.
Precisely. The total high-dimensional prediction breaks down into the local base-level STO, just the movement multiplied by these separate high-level prediction kernels for things like hydration and a timing function. This factorization is what makes planning in these dynamic, coupled systems tractable.
That efficiency gain seems like it would immediately lead to that second property we wanted, modularity, reusability, which the paper calls sublimation.
Sublimation is a fantastic concept for reusing knowledge. Because the system is modular, you can solve a simplified, abstract version of the problem first. So, for instance, you can solve just the logical task, the sequence of keys and doors, completely separate from the messy physical world.
So you run the logic puzzle in a kind of clean sandbox first.
Exactly. And you get the sublimated feasibility knowledge. It's basically the perfect abstract plan for the logical steps. And this knowledge then acts as a verifiable upper bound on the feasibility of the full messy problem.
And what does that perfect abstract plan actually do? Does it speed things up?
Oh, absolutely. That reusable sublimated knowledge gets passed down to the base level. So when the honey badger is exploring the physical world, if the logical plan says this path is impossible, it doesn't even bother exploring it physically. It prunes all these infeasible branches from the search tree really early on.
Massive gains in efficiency and verification. Okay, so we've built these factorized, verifiable, composable STOKs. The last step in the engine is putting them all together into the goal kernel.
The goal kernel is the culmination of all of this. It's the central planner that maps an initial high-dimensional state to a final state and time under some option. It lets the agent forward plan at the level of goals, not just tiny actions, which is way more powerful.
So let's use the honey badger one last time to really nail down the verification benefit here. The badger has to get a key before the honey, or a bear wakes up. And at the same time, it can't run out of water.
So the goal kernel aggregates all those specific event probabilities. The STOKs are explicit, so the agent doesn't just get a final score, it gets a breakdown. It can see, okay, total goal success probability is maybe 0.3, but the constraint violation probability dying of thirst is 0.7.
It can literally forecast the risk of death, not just the potential reward.
And this information flows both ways. High-level predictions, like running out of water, get passed down to call risky base-level options. And conversely, the base-level STOK predictions, how long it actually takes to get to the lake, are passed up to forecast the high-level dynamics.
That kind of multi-level verifiable planning is it's impossible with standard reward maximization. The data just isn't there.
It's gone. And the practical result is efficiency. The paper shows how, by treating a sequence of options as one abstract action, the search depth just plummets. You go from searching dozens of little physical steps to just a handful of abstract verifiable options.
Temporal abstraction meets verifiability. That's the magic.
That's the magic of the goal kernel.
So let's zoom out. The research shows that OKBEs give us a fundamental, mathematically solid alternative to the reward hypothesis. It delivers on compositionality, modularity, and interpretability by keeping all that detailed event info in the STOKs. But there's a much deeper connection here, isn't there? Something linking this planning engine to the concept of value itself.
Yes. This is the normative conclusion of the whole framework. Because the goal kernel is factorized and interpretable, it allows for a natural theory of intrinsic motivation to emerge, and it's one driven not by external signals, but by this concept of empowerment.
Empowerment, that's a term that gets thrown around a lot. How does this paper define it in a concrete way that an AI can actually use?
Formally, it's defined using Shannon channel capacity. But conceptually, it just quantifies the agent's freedom, its ability to reliably cause a variety of different observable changes in its world. How many different paths can I reliably choose from that lead to different outcomes?
So, the agent is calculating its own intrinsic worth based on its perceived control over its environment.
Precisely. Because the goal kernel is so modular, an agent can actually calculate empowerment, gain the difference in empowerment between two states. So imagine the honey badger finds a key. That key doesn't give it plus 5 points.
Right.
It changes the structure of the world. And the AI can calculate the value of finding that key by measuring how much it increases its future freedom, its range of reliable choices.
So it's the AI making an intrinsic agent relative value judgment based on the world structure, not on some number it's fed. It's self-justifying its own goals.
Exactly. It allows for derived, contextually computed value. It justifies goals based on its own ontology of freedom, not because an engineer told it what's valuable. That level of intrinsic motivation is, I think, crucial for anything we call true general intelligence.
That is a phenomenal pivot. It moves us from building robots that chase high scores
Yeah.
to designing minds that seek control and knowledge.
And that pursuit of knowledge, that empowerment gain, can become a goal in and of itself.
So what does this all mean for the immediate future? The research has, I think, beautifully shown that OKBEs make a previously intractable problem representable, but the bottleneck is still there, right? It's efficiently solving that final option tree search, especially when things get really uncertain.
Yes.
So a key theoretical problem for you to mull over is this. How do you find fast, efficient ways to create a risk-calibrated set of SDX and options for really complex multi-goal problems under uncertainty? The foundations have been laid, but the engineering challenge is really just beginning.